Hello everyone, my name is Cody Newell and this is my final project presentation for ADTA 5340. This project covers 6 parts spanning machine learning strategy, data pre-processing, supervised learning, unsupervised learning, and model comparison. Let's get started. Here's a quick overview of what we'll be covering today. We'll start with machine learning strategy for a healthcare organization, then move through data pre-processing, 3 modeling sections covering regression, classification, and clustering, and finish with a model comparison. Part 1 asks us to design a machine learning strategy for a company of our choosing. I chose to base mine on a skilled nursing facility environment because that's the field I work in, which gives me first-hand knowledge on the operational challenges involved. The fictional company I created is called West Park Health and Rehabilitation Center in McKinney, Texas. West Park is a skilled nursing facility offering short-term rehab, long-term care, and memory care. The key detail on this slide is the technology setup. The nursing side runs on an electronic health record system called Point-Click Care, and therapy runs on NetHealth. These two systems don't communicate with each other, and that integration gap is the central technological challenge the entire strategy is built around. There are 5 key business drivers that make machine learning adoption both timely and necessary for a facility like West Park. First, CMS value-based purchasing. Medicare financially penalizes skilled nursing facilities with high 30-day readmission rates. If a patient leaves and comes back to the hospital within 30 days, the facility takes a hit. A predictive model that flags at-risk patients before discharge can prevent that. Second, PDPM reimbursement. Since 2019, Medicare payment is based on clinical complexity rather than therapy minutes. Documentation accuracy directly affects how much the facility gets paid. Machine learning can improve that accuracy. Third, and this one is unique to therapy staff, the GG documentation burden. CMS requires functional assessments to be completed at admission, at a quality indicator time point, and again at discharge. That's 3 times per patient stay. At West Park, therapy staff are held to a 92% productivity standard, meaning almost all of your scheduled time has to be billable. Completing a GG assessment eats into that standard. An ML scheduling tool that tells you the optimal time to complete those assessments protects your productivity numbers without sacrificing compliance. Fourth, staff turnover. SNF turnover rates for CNAs and LVNs nationally exceeds 50% annually. Each departure costs thousands in recruiting and onboarding. Predicting who's about to leave before they resign gives management a window to intervene. Fifth, referral competition. Hospital discharge planners route patients based on STARS ratings. Better outcomes driven by machine learning translates directly into better ratings and more referrals. Now let's look at the 5 machine learning use cases I designed for West Park. First, readmission risk prediction. Medicare penalizes facilities when a patient returns to the hospital within 30 days. This model scores every active patient daily for that risk and flags high-risk cases for care team review. Second, therapy outcome forecasting. Using admission assessment scores and diagnosis, the model predicts what patient's recovery should look like by discharge, giving the therapy team a data-informed target from day 1. Third, GG workflow optimization. Medicare requires therapists to complete standardized functional assessments multiple times per patient stay, but therapists are also held to strict productivity standards where most of their time must be billable. That's a direct conflict. This model predicts the optimal time windows for completing those assessments so productivity isn't sacrificed. Fourth, staff retention modeling. SNF turnover exceeds 50% annually. This model uses HR and scheduling data to predict resignations within 60 days so management can intervene before someone walks out. Fifth, quality indicator clustering. Medicare publicly rates every SNF on a quality metric that directly affects referral volume. K-means clustering identifies documentation patterns that are quietly hurting those scores. Now let's talk about how this actually gets built and deployed. On the technology side, the foundation is a cloud-based data warehouse pulling from Point-Click Care and NetHealth through nightly data pipelines. Model development uses Python with scikit-learn, pandas, and NumPy. Outputs are delivered through role-based dashboards so clinical staff never interact with raw model outputs directly. A therapist sees the recommended time window at shift start, and a charge nurse sees a risk flag at shift change. Implementation happens in 3 phases over 18 months. Phase 1 builds the data foundation and trains staff. Phase 2 pilots the models at West Park before any network-wide rollout. Phase 3 is a full deployment, model retraining protocols, and ROI reporting back to the board. Moving on from the strategy section, part 2 is where we get into the actual data work. For this part, we were given a real data set from the Austin Animal Shelter in Austin, Texas, collected between 2013 and 2020. Animal shelters collect data on every animal that comes to their door, and being able to predict outcomes like adoption, transfer, or euthanasia could help shelters make better decisions about resource allocation and which animals need extra attention to improve their chances. Our job in part 2 is to pre-process that data to get it ready for modeling. The sheltered animals dataset contains 95,367 records spanning about 6.5 years. It came with 10 attributes covering things like animal ID, intake dates, age, breed, color, sex, and the target variable, which is the outcome type, whether the animal was adopted, transferred, returned to its owner, euthanized, and so on. Before any modeling could happen, the data needed significant pre-processing. Several attributes were redundant or irrelevant for prediction. The age field was stored as text rather than numbers, and there were missing values and invalid entries that needed to be handled. All of this is what part 2 covers. Here are the 8 pre-processing steps I applied to the dataset. Step 1 was loading the data. The CSV file had no header row, so column names had to be defined manually, and I used the index column equals false parameter as required by the course to prevent pandas from misreading the column as an index. Step 2 was an initial inspection to understand data types and identify missing values. I found 13 missing values spread across 3 columns. Step 3 was removing irrelevant columns and invalid entries. 4 columns were dropped. The animal ID, which is just an identifier, 2 redundant date columns, and the raw birth date since age was already captured elsewhere. I also found 118 records where age was listed as 0 years, which is an invalid placeholder entry, and removed those before converting the age field. Step 4 was inspecting the age field before transforming it. The assignment described the values as either years or months, but the actual data had 4 time units: years, months, weeks, and days. So the conversion function had to handle all 4 of those cases. Step 5 converted age from text to numeric months. Years were multiplied by 12, months kept as is, weeks divided by 4.33, and days divided by 30.44. Step 6 dropped the remaining missing values, which was only 10 rows out of over 95,000, less than 0.02% of the data. Steps 7 and 8 were a final clean inspection and exporting the clean file. The final dataset came out to 95,239 records across 6 attributes with no missing values. Now that the pre-processing is out of the way, let's get into the actual machine learning. An abalone is a type of shellfish, and researchers can determine its age by counting the rings inside its shell, similar to how you'd count the rings on a tree. The dataset we're working with contains physical measurements of abalones, and the goal is to build a model that can predict age from those measurements without having to cut the shell open and count the rings manually. Before building any model, exploratory data analysis is required to understand what we're working with. The abalone dataset contains 4,177 records and 9 attributes. The target variable is rings, and the age is calculated as rings plus 1.5 years. A few things stood out during the EDA. There were no missing values, which is relatively clean for a real-world dataset. However, I did find 2 records where the height measurement was exactly 0, which is physically impossible for an abalone with meat in its shell. These were flagged as invalid entries. The sex attribute had 3 categories: male, female, and infant, which needed to be encoded to numeric values for modeling. Looking at the rings distribution on the right, you can see it's roughly normally distributed, centered around 9 to 10 rings, with the right tail extending out to 29. That's a well-behaved target variable for regression, which tells us the modeling task is reasonable, even if it won't be perfect. Pre-processing for the abalone dataset was minimal. The two records with a height of 0 were removed since they represent invalid measurements. The sex attribute was encoded using label encoding, mapping female to 0, infant to 1, and male to 2. After that, all 9 attributes were fully numeric and ready for modeling. The clean data set was exported as abalone clean.csv with 4,175 records and no missing values. For this data set, the goal is to predict a continuous numeric value, the number of rings, which makes this a regression problem. I selected decision tree regression for several reasons. First, the dataset contains both categorical and continuous numeric features. Decision trees handle that mix without requiring any scaling or normalization, unlike distance-based models like k-nearest neighbors. Second, decision trees are non-parametric, meaning they don't assume any particular distribution in the data. An unconstrained decision tree with no depth limit grew to 27 levels deep with nearly 2,000 leaf nodes. When I tested it on the test set, the R-squared was only 0.144, which is a clear sign of overfitting. The model memorized the training data but couldn't generalize the new records. To fix this, I used the grid search CV with 10-fold cross-validation to find the optimal maximum depth. I tested depths of 3, 5, 7, 10, 15, 20, and unconstrained. The results showed that the maximum depth of 5 produced the best mean cross-validated R-squared of 0.4811. That's the value I used for the final model. With a max depth set to 5, the model was evaluated on the held-out test set of 835 records. The R-squared came in at 0.5267, meaning the model explains about 52% of the variance in ring count. The RMSE was 2.32, which means on average predictions are off by about 2.32 rings, or roughly 2.32 years of age. 52% might not sound impressive, but abalone age prediction is a known difficult problem in the machine learning literature. The high biological variability in ring counts among same-age abalones puts a natural ceiling on how well any model can perform using physical measurements alone. An R-squared near 0.5 is actually consistent with published research on the dataset. The 10-fold cross-validation confirmed this with a mean R-squared of 0.4847 and a standard deviation of only 0.0346, which tells us the model is consistent across different subsets of the data and not just getting lucky on one particular split. As part of the assignment, I created 2 new records with reasonable attribute values and used the trained model to predict their ages. Record 1 represents a large adult male abalone with measurements toward the upper range of the dataset. The model predicted 10.5 rings corresponding to an age of 12 years. Record 2 represents a smaller infant abalone with measurements toward the lower range. The model predicted 6.15 rings corresponding to an age of about 7.65 years. Both predictions fall within plausible biological ranges given what we know about the dataset distribution, which gives us confidence the model is producing reasonable outputs even on records it hasn't seen before. The abalone dataset was a regression problem because we were predicting a continuous numeric value. Part 4 shifts to classification, where the target variable is binary. We're working with a census dataset, and the goal is to predict whether an individual's annual income is greater than or less than $50,000. The adult salary dataset contains nearly 49,000 records collected from a 1994 U.S. Census survey with 15 attributes covering demographics, employment, education, and financial information. A few things stood out during the EDA. First, the dataset uses a question mark character to indicate missing values rather than leaving cells blank, which required a specific handling approach during pre-processing. Second, and this is visible in the income chart on the right, the dataset has a significant class imbalance. About 76% of records fall in the less than or equal to 50,000 category, and only 24% are above 50,000. That imbalance is going to affect how the model performs, and this is something we'll come back to when we're interpreting the results. Looking at the age distribution on the left, you can see it peaks around 30 to 35 years and has a right tail, which is typical for a working age population. One other data quality issue I found during the EDA was the income column had 4 distinct values instead of 2. Some entries had trailing periods and leading white space that needed to be cleaned before the column could be used as a target variable. Pre-processing for this dataset involved 4 main steps. First, I cleaned the income column by stripping the leading white space and removing the trailing periods, which consolidated the 4 values down to the expected 2. Second, the final weight column was removed. This is a census survey weighting attributes that has no predictive value for income classification and was explicitly identified for removal in the assignment instructions. Third, the question mark missing values were replaced with the NaN and the affected rows were dropped. This removed 3,620 rows, leaving 45,222 records. The final count is lower than the sum of the individual column counts because some rows had question marks in multiple columns simultaneously. Fourth, all categorical columns were label encoded. This includes employment type, education, marital status, occupation, relationship, race, sex, country, and the target variable income. After encoding, all 14 remaining attributes were fully numeric and the clean dataset was exported. For this binary classification problem, I selected decision tree classification as the primary model for the same reasons as Part 3. It handles mixed feature types without scaling, it's non-parametric, and it was covered in the course material. Grid search CVE with 10-fold cross-validation identified max depth of 10 as the optimal parameter with a mean accuracy of 85.18%. I also added random forest as a secondary model to validate the decision tree results. Since both of my new records predictions came out as less than or equal to 50,000, which was unexpected for a high earner profile, I wanted to see if a more powerful ensemble method would produce a different outcome. Random forest is covered in the course lectures and combines multiple decision trees using majority voting. I applied class weight balanced to address the 76-24 class imbalance by giving the minority class more weight during training. As we'll see in the results, both models agreed on the predictions, which actually strengthened the conclusion that the class imbalance is the dominant factor here rather than a limitation of any single model. Here are the results of both training models side by side. The decision tree achieved 85.12 accuracy on the test set and 85.17% on the cross-validation with a standard deviation of only 0.0037, which is remarkably consistent across all 10 folds. The random forest came in at 84.8% test accuracy and 84.01% cross-validation mean. So the decision tree actually outperformed random forest on this data set, which is somewhat counterintuitive. The explanation is that the class weight balanced parameter we applied in random forest penalizes the majority class aggressively across all 100 trees, which slightly reduces overall accuracy while trying to improve minority class detection. Looking at the new record predictions, both models predicted less than or equal to 50,000 for both records. As I mentioned, this is consistent with the 76-24 class imbalance. The dataset reflects a population where the majority of people earn under 50,000, so both models learn to be conservative about predicting the minority class. When two different model architectures agree on the same prediction, it actually gives us more confidence that the result reflects the true patterns in the data rather than a flaw in either model. Parts 3 and 4 were both supervised learning. We had labeled data and trained models to predict known outcomes. Part 5 shifts to unsupervised learning, where there's no label to train on. Instead, we're letting the algorithm find natural groupings in the data on its own. The data set here is a car evaluation data set, and we're using k-means clustering. The car evaluation data set contains 1,728 records and 7 attributes. Every attribute is categorical and ordinal, meaning each one has a natural ranking from lowest to highest. Things like price going from low to very high, safety going from low to high, and so on. One thing that stood out immediately during ADTA is that this dataset is synthetically generated. Every feature attribute is perfectly uniformly distributed. exactly 432 records per category for some attributes and 576 for others. That level of perfect balance doesn't occur in real-world collected data. It was constructed to cover every possible combination of feature values systematically. The evaluation label on the right tells an important story. About 70% of the records are classified as unacceptable. Only 22% are acceptable, and good and very good combined make up less than 8%. That heavy skew towards unacceptable is going to be a central challenge for clustering, which we will discuss in the results. Two attributes also had text-based abnormal values. Doors had a value of 5 more instead of a number, and passengers had a value of more. Both were handled during encoding. Because k-means requires numeric input, all categorical variables were converted to numbers using ordinal encoding. The key reason I chose ordinal encoding over one-hot encoding is that every attribute in this dataset has a natural order. Low price is genuinely less than medium price, which is genuinely less than high price. Ordinal encoding preserves that relationship in the numeric representation. One-hot encoding would treat each category as completely independent, which would lose that meaningful ordering and distort the distance calculations k-means relies on. The abnormal text values were handled as part of this step. 5 more for doors was mapped to 3, and more for passengers was mapped to 2, placing them in their appropriate ordinal positions. For the model, I selected k-means clustering, which is an unsupervised algorithm covered in the course material. The evaluation column was set aside and not given to the model during training. In unsupervised learning, the algorithm has to discover patterns on its own without being told what the answer is. To find the optimal number of clusters, I used the elbow method, which you can see in the chart on the right. I tested k values from 2 to 10 and plotted the inertia at each value. The curve begins to flatten around k equals 4, and conveniently the evaluation label has exactly 4 categories: unacceptable, acceptable, good, and very good. So k equals 4 was selected. Here are the results from the k-means model. The 4 clusters came out reasonably balanced in size, ranging from 378 to 459 records each. Looking at the centroid table, something interesting emerged. K-means primarily differentiated the clusters based on price, maintenance, and doors. The passengers, luggage, and safety features all converged to a centroid value of exactly 1 across all 4 clusters, meaning those 3 features didn't contribute meaningfully to the distinguishing of the groups. Cluster 2 is the most distinct. It has the highest price and maintenance centroids and is almost entirely composed of unacceptable evaluations with 0 good or very good records. That makes intuitive sense. Expensive cars with high maintenance costs are going to be unacceptable to most people. Cluster 3, on the other hand, has the lowest maintenance centroid and has the highest proportion of good and very good evaluations relative to its size. However, the overall picture is complicated by the 70% unacceptable dominance in the dataset. Every single cluster is dominated by unacceptable evaluations. The silhouette score of 0.1578 confirms weak cluster structure with significant overlap. This is expected given the synthetic and perfectly balanced nature of the dataset. K-means works best when there are natural, well-separated groupings in the data, and this data doesn't have that. I created 2 new records to test the model. Record 1 represents a budget-friendly car with low price, low maintenance, 4 doors, and high safety. The model assigned it to Cluster 3, which has the lowest maintenance centroid and the highest proportion of good and very good evaluations. That's a reasonable assignment. Record 2 represents an expensive car with very high price, very high maintenance, 2 doors, and low safety. The model assigned it to Cluster 2, which is almost entirely unacceptable evaluations. Again, that makes intuitive sense. The PCA visualization at the bottom shows the cluster plotted in 2 dimensions after reducing the 6 features down to 2 principal components. Those 2 components only explain 43.5% of the total variance, which means we're losing a lot of information in this visualization. And the grid-like pattern you see is a direct result of the synthetic nature of the dataset. Every possible feature combination exists exactly once, so the data points form a perfect grid rather than a natural organic cluster you'd see in real-world data. This result is honest and instructive. Not every data set is well suited to every algorithm. K-means on a synthetic, perfectly balanced data set with a heavily skewed target label is going to produce weak clustering, and that's exactly what the silhouette score confirmed. For part 4, we step back from individual models and compare them directly against each other. We have two comparisons: linear regression versus decision tree regression on the abalone dataset, and logistic regression versus k-nearest neighbors on the adult salary dataset. For the regression comparison, I trained both linear regression and decision tree regression on the same abalone dataset using the same 80-20 train test split. Looking at the results, linear regression outperforms decision tree on both metrics. The test set R-squared is 0.5571 for linear regression compared to 0.5267 for decision tree. The RMSE is 2.2481 versus 2.3240, meaning linear regression predictions on average are about 0.08 rings closer to the actual value. The cross-validation results tell the same story. Linear regression achieves a mean R-squared of 0.5156 across 10 folds compared to 0.4847 for decision tree. Linear regression does show slightly more variability across folds with a standard deviation of 0.0483 versus 0.0346, but it maintains a higher average performance throughout. The chart makes the difference clear visually. Linear regression is consistently ahead on both test set R-squared and cross-validated mean R-squared. For the prediction comparison, I used the same record from part 3. A large adult male abalone with measurements toward the upper range of the dataset. Linear regression predicted 11.43 rings, corresponding to an age of 12.93 years. Decision tree predicted 10.5 rings, corresponding to an age of 12 years. The two models differ by 0.93 rings, or about 11 months of age. Since the models disagree, we used the R-squared comparison to determine which prediction to trust. Linear regression had the higher test set R-squared and the higher cross-validated mean R-squared, so the linear regression prediction of 12.93 years is the preferred estimate for this record. For the classification comparison, I trained both logistic regression and k-nearest neighbors with k equals 7 on the same adult salary dataset using the same 80-20 split. Both models required feature scaling since they're sensitive to the magnitude of input values, so standard scalar was applied before training. KNN outperforms logistic regression on overall accuracy, 83.13% versus 82.17%. But the more meaningful difference is in the recall for the greater than 50,000 class. KNN correctly identifies 60% of high earners compared to only 46% for logistic regression. Given the 76-24 class imbalance in the dataset, the ability to detect the minority class is the important distinction. The cross-validation results confirm this consistently. KNN achieves a mean accuracy of 83.33% across all 10 folds compared to 82% for logistic regression. And KNN outperforms logistic regression in every single fold, which is strong evidence that the performance difference is reliable and not due to chance. The chart shows the graph cleanly. KNN is ahead on both test accuracy and cross-validated mean accuracy. For the prediction comparison, I used the same new record from part 4. A 45-year-old male, private employer, bachelor's degree, married, executive managerial occupation with capital gains of $5,000 working 50 hours a week in the United States. Both logistic regression and KNN predicted greater than 50,000 for this record. That's notable because the decision tree in part 4 predicted less than or equal to 50,000 for the same record. The fact that two different model architectures, logistic regression and KNN, both agree on greater than 50,000 gives us more confidence in that prediction than the decision tree result alone. Since both models agree there's no conflict to resolve, but based on the higher accuracy and better minority class recall, KNN is the preferred model and greater than 50,000 is the preferred prediction for this record. To wrap up, here's a quick summary across all 6 parts. Part 1 was a machine learning strategy for skilled nursing facility. Part 2 pre-processed the animal shelter dataset. Parts 3 and 4 covered supervised learning, regression on abalone, and classification on adult salary. Part 5 was unsupervised clustering on the CAR evaluation dataset. Part 6 compared 4 models head-to-head with linear regression and KNN coming out on top in their respective categories. Thank you for watching. This has been my final project presentation for ADTA 5340.